Context-aware deployment of the on-off algorithm. Strategic use of discontinuous control in modern process applications. The on-off algorithm, often considered the simplest control strategy, provides binary logic that toggles the manipulated variable between fully on and fully off states. While inherently limited by its discontinuous nature, it excels in certain industrial applications where full-range actuation, safety logic, or basic process control is sufficient. Core characteristics of on-off control. Binary output action. The controller operates in a two-position mode, 0% off or 100% on, typically engaging solenoid valves, electric heaters, or relays. No throttling capability. The controller does not modulate the final control element. It switches between extreme positions, making it unsuitable for applications requiring precision or continuous adjustment. Built-in oscillatory nature. The process variable never stabilizes at a fixed set point but continuously cycles around it. The amplitude and frequency of cycling are driven by process dead time, capacitance, and thermal or mass inertia. Deadband integration. Controlling excessive switching. To mitigate rapid switching, which accelerates wear and may lead to instability, a differential gap, also known as deadband, is implemented. The controller only changes output when the process variable moves outside this gap. This reduces unnecessary cycling and limits the frequency of actuator engagement. The gap is typically configured as a percentage of the measurement span and is adjustable for specific process conditions. Gain and phase behavior. Extremely high gain, small changes in the input, measurement, or error lead to full-scale changes in output. This high sensitivity can make the system react to minor fluctuations or noise. Nominal phase shift. The ideal on-off controller introduces no dynamic lag. However, in practice, the inclusion of a dead band alters the system response and may affect oscillation amplitude and cycle time. Application scenarios for on-off control. Processes with low precision demands, useful in temperature or level control where large process volumes naturally buffer oscillations, such as in storage tanks or thermal systems. Safety and emergency shutdown, ESD, ideal for binary, fail-safe operations, such as cutting off fuel or pressure sources when critical process parameters are violated. Simple or discrete operation cycles, effective in start-stop systems, tank filling, air compressors, or batch-based production systems. Hardware-limited environments, especially suitable for systems where full-scale analog or digital control infrastructure is cost-prohibitive or unnecessary. Integration into broader automation architectures, embedded in cascade skate structures, acts as a terminal actuator logic, responding to inner loop signals, or as a safety interlock in flow or pressure cascade pairs. Supervisory decision layer. Higher level controllers or AI systems may invoke on-off actions based on diagnostics, safety margins, or predictive models. Fallback or override mode serves as a protective boundary to disengage modulated control loops when a process goes outside safe or normal operating conditions. Advantages of on-off control: extremely simple and robust design, low cost with minimal instrumentation, requires not uning or parameter adjustment, suitable for applications where full-range actuation is desired, compatible with protective and binary functions. Limitations of on-off control: cannot modulate or balance a supply with process demand, controlled variable always oscillates, steady state is never achieved, high actuator wear due to frequent state transitions, sensitive to noise and vibration unless deadband, eyes applied poor performance in high-speed or high-precision applications. Conclusion: on-off control is not obsolete, it is purpose-built for specific classes of process behavior. Whether in basic level control, interlock systems, or ESD logic, it provides deterministic binary action that is easily understood, implemented, and maintained. With appropriate configuration, especially through differential gap tuning, it delivers reliable performance within a broader adaptive or cascade-enabled automation framework. Strategic deployment of the proportional algorithm, balancing supply and demand through proportional amplification. Proportional control represents the foundational algorithm in continuous feedback regulation. Unlike on-off controllers, which operate in binary states, proportional controllers adjust the control output in a continuous manner relative to the size of the error. The result is smoother, more responsive control capable of balancing supply and demand in real time. though not without its trade-offs, particularly the presence of steady-state offset. Core characteristics of proportional control. Proportional output response. The controller output changes in direct proportion to the process error, difference between set point and measured variable. Larger errors yield larger corrective actions. Linear control behavior. The proportional action behaves like a variable amplifier. Its effect is governed by a gain setting or its reciprocal, the proportional band, PB. Offset presence at steady state. Proportional control alone cannot eliminate the steady state error. Once the process stabilizes, a fixed error, offset, often remains unless corrected by other modes. Functional mechanics and terminology. Proportional gain, G, determines how aggressively the controller reacts to an error. A high gain results in a stronger response but can lead to instability if not tuned properly. Proportional band, PB, represents the range of input change required to drive the output across its full range. A narrow PB implies high gain, a wide PB implies lower gain. Bias term, a fixed or manually set output used when error is zero. Allows the controller to provide a baseline output even in the absence of deviation. Without bias, proportional control cannot function when error equals zero. Behavioral dynamics and performance traits. Error-driven output adjustment. The controller continuously modifies output to reduce error, but settles at a non-zero value due to the absence of integral action. Gain-offset relationship. The higher the gain, or the narrower the PBB, the smaller the steady-state offset. However, excessive gain may lead to oscillation or instability. Linear process compatibility. Proportional control works best in self-regulating processes with moderate dynamic gain, such as pressure or flow systems with relatively fast responses. Application guidelines for proportional-only control. Suitable when offset is acceptable. Proportional-only control is viable where minor steady-state deviations can be tolerated, such as in surge tanks or low-precision mixing processes. Ideal for low-gain, high-capacity systems. In large thermal or level systems with slow dynamics, the natural buffering effect of the process helps minimize the impact of offset. Effective for processes with infrequent load changes. When disturbances are slow or seasonal, the fixed bias can be manually adjusted to compensate for new steady-state conditions. Advantages of proportional control provides immediate and continuous corrective action, simple to implement and easy to tune, reduces oscillation, and improves response time compared to on-off. No inherent instability in most linear or self-regulating systems. Limitations of proportional control. Always operates with a residual steady-state error offset, cannot track slow or drifting load changes accurately, requires process-specific gain tuning to balance performance and stability. Not ideal for systems needing precise set point maintenance. Hash process type compatibility. Good fit for self-regulating processes, e.g. flow, pressure loops, large capacity processes with low dynamic gain, situations where minor error is not critical. Poor fit for non-self-regulating or integrating systems, processes requiring zero steady-state error, systems with highly variable loads or tight tolerance demands. Conclusion. Proportional control offers a powerful step up from on-off logic, providing smooth, continuous correction that balances performance and simplicity. While offset remains a limitation, its immediacy and clarity of response make it a valuable mode in many industrial control scenarios, especially when paired with manual biasing or embedded in more advanced multi-mode control strategies. Strategic deployment of the integral algorithm, eliminating steady-state error through accumulated correction. The integral control algorithm offers a powerful solution to a fundamental limitation of proportional control, its inability to eliminate steady-state error, offset. By continuously integrating the process error over time, integral control ensures that the manipulated variable evolves until the error reaches zero. This persistent corrective nature makes it indispensable in applications demanding high-precision regulation and steady-state accuracy. Core characteristics of integral control: time-accumulated error correction. The controller output increases or decreases based on the accumulated deviation between the set point and the measured variable over time. Zero steady state error. Integral action continues to adjust the output until the error is fully eliminated, making it ideal for set point tracking and processes requiring precise final values. Self-biasing behavior. Unlike proportional-only control, which relies on a fixed bias, integral control inherently adjusts its output to match process load, eliminating the need for manual tuning of bias. Functional mechanics and tuning parameters. Integral time I defines how aggressively the controller responds to error over time. It is typically expressed in minutes per repeat, min rep, or repeats per minute, rep per min, depending on the controller type. Ramp output behavior. The integral controller output ramps continuously as long as a non-zero error exists. The ramp rate is proportional to the error magnitude and inversely related to the integral time setting. Direction and polarity. Reverse or direct action must be appropriately configured to ensure the controller increases or decreases output in the correct direction when error is detected. Behavioral dynamics and system impact. Persistent adjustment. Even a small, sustained error will cause the output to continue moving until the deviation is nullified. Slow response character. Integral control introduces additional lag into the system. The longer the integral time, the slower the response, but too short a setting can lead to instability. Risk of windup. When the output saturates, e.g. hits valve limits, but the error remains, the controller can wind up, accumulating excessive internal correction that causes overshoot once normal operation resumes. SATA application guidelines for integral-only control. Useful for precise set point tracking. Processes where set point error is unacceptable, such as flow loops, temperature trimming, or blending systems, benefit from integral action. Effective in slow or buffered loops. In slow reacting systems, such as background level or composition trim loops, integral control can maintain high accuracy without needing fast response. Inappropriate for non-self-regulating processes. Integral-only control applied to integrating NSR systems, such as tanks with pure capacity and no natural feedback, will always lead to continuous cycling or instability. Advantages of integral control: eliminates offset completely at steady state, automatically adjusts output to match process load, reduces long-term integrated error IAE, acts as a natural filter, smoothing noisy signals, minimal tuning effort in simple, like self-regulating systems. Limitations of integral control: slower to respond compared to proportional or derivative control, cannot stand alone in NSR or integrating processes, leads to continuous oscillation, prone to wind up if actuator limits are reached, adds lag, which may degrade responsiveness in fast systems. Process type compatibility: ideal for self-regulating systems requiring zero steady-state error, slow, stable loops like flow control, temperature trim, or ratio feedback, loops where load changes are gradual and precision matters. Avoid for pure capacity or integrating processes without natural feedback, systems with high measurement noise or actuator limits, situations requiring fast disturbance rejection. Conclusion: the integral algorithm is a cornerstone of precision control, capable of eliminating residual error and maintaining exact set point performance. Its persistent corrective behavior ensures accuracy, but it must be applied with caution. Understanding process dynamics, especially time constants and self-regulation, is critical when determining whether integral-only control is appropriate. When used strategically or in combination with other modes, e.g. PI or PID, integral action becomes a key enabler of high-performance control loops. Strategic deployment of the proportional plus integral PI algorithm, combining speed and precision for robust set point control. The PI algorithm integrates the immediacy of proportional action with the accuracy of integral correction, making it one of the most widely used control strategies in industrial automation. It balances responsiveness with long-term precision, addressing both transient errors and steady-state offset without the complexity or sensitivity of derivative action. This makes PI control suitable for the majority of regulatory process applications. Core characteristics of PI control: dual mode response. The proportional mode reacts instantly to changes in error, while the integral mode accumulates error over time to drive it to zero. Offset elimination with finite response time. Unlike proportional-only controllers that operate with residual error, the integral component of PI ensures zero steady-state offset, typically with a faster response than integral-only systems. Dynamic load tracking. As load conditions shift, the integral term self-adjusts the control output to match the new steady-state requirements without operator intervention. Functional mechanics and algorithm behavior. Controller output formula. The PI controller produces output using the equation M equals 100 PB times E plus 100 PB 1 ver I, E dt tura, where minus PB is the proportional band, I is the integral time, E tura is the error between set point and measurement. Gain coupling. Both proportional and integral contributions scale with the same gain term, allowing unified tuning without altering the relative phase contributions. Continuous correction until zero error. The integral portion ensures that control action does not stop until the measured variable equals the set point exactly. Performance traits and operational considerations. Fast initial response. The proportional term delivers an immediate correction proportional to the error magnitude, stabilizing the system quickly after a disturbance. Gradual final tuning. The integral term takes over after initial proportional action, adjusting output gradually to remove any remaining offset. Wind-up risk. If error persists while the actuator is saturated, e.g. valve fully open, the integral term can accumulate excessively, leading to overshoot once control resumes. This necessitates anti-wind-up protection. Application guidelines for PI control. Ideal for loops requiring set point accuracy and stability. Applications such as temperature control, flow loops, and pressure regulation benefit from PI's ability to combine speed and precision. Suited for most self-regulating processes, especially effective in processes where dead time and capacity are moderate and where load changes are common but not extreme. Avoid for very fast or noisy systems. In high-speed loops or those with substantial measurement noise, the integral mode may cause sluggishness or instability without proper filtering or tuning. Chart advantages of PIC control: eliminates steady-state offset while maintaining acceptable speed, provides both immediate and sustained corrective action, easier to tune than full PID controllers, reduces integrated error and improves loop efficiency, versatile across a broad range of industrial applications. Limitations of control: slower than proportional only in reaching steady state, can exhibit overshooter oscillation if not tuned properly, susceptible to wind-up in systems with actuator saturation, not ideal for processes needing aggressive preemptive control, use derivative in those cases. Process type compatibility. Best suited for self-regulating thermal, flow, or level loops, loops where both error elimination and moderate speed are required, systems where PID is too aggressive or sensitive. Less suited for integrating processes may require PI with reset bias protection. Noisy loops lacking sufficient filtering, very slow or very fast processes with extreme dynamic ranges. Conclusion: PI control offers the optimal compromise between simplicity and control performance. It is robust enough to handle a wide variety of process dynamics while providing the key benefits of offset elimination and rapid stabilization. As a default algorithm in many control systems, its correct application and tuning are essential for achieving efficiency, product quality, and operational stability in modern process automation.